All right, guys, this is going to seem really strange, but because this is how my day is going, the video, for some reason, even though here, as you can see, it says it's 21 minutes. When I upload it to YouTube, it's only 11 minutes. So I'm going to try this again by just recording the video. So don't mind me. It's going to just be playing, and hopefully I will then get a full video from it. Of our 1.5 lecture. I'm going to tell you I'm going to do something a little differently. I'm having trouble when I have my document camera connected to my Chromebook. It won't record audio. So I'm going to do the whole thing, explaining all the parts for today. And then I'm going to plug in my hover cam and hope that the volume works. But either way, it'll just be for the examples, and I'm going to try the voiceover feature in Edpuzzle to go through those examples for you. Hopefully that works out. That's the plan. So if it's a little awkward later on, that's what I'm doing. All right, so we are talking atomic structure and electron configurations. Almost none of this is new from last year, but since this was when we were in hard quarantine, I thought we should talk a little bit about it. And kind of teach it like I haven't done it before. I'm going to go through everything, but some of it not very in depth. Like there's some things at the very beginning, atomic structure, it's important to understand, and there's things that you need to know, but you don't need to have memorized like what scientists did what. Okay, history is not part of the AP test. So one of the only new things is going to be what's called Coulomb's law, and that's what we're going to talk about here. So our Rutherford model of the atom. This is the model that decided is the wrong thing, that where they discovered that the nucleus was a dense positive center. Okay, so they didn't necessarily know at the time that they had neutral neutrons. They just knew that most of the mass of a atom was contained in the center, and it was very dense compared to the mostly empty space around it, and it was positively charged. They knew that there were negative electrons that were orbiting. They didn't know how, but they just there's electrons on the outside, and that they were governed by Coulomb's law. So Coulomb's law states that the force between two charged particles, Q1 and Q2, is inversely proportional to the square of the distances between them. So that sounds like a lot. So what does that mean? So Coulomb's law says that two charged particles are going to have more of an attraction if their charge is larger. So a +2 and a -2 are going to be more attracted to each other than a +1 and a -1. And that attraction will decrease as you increase distance. Okay. So a +2 and a -2, super attracted to each other when they're really close together. You pull them apart, and they're not as attracted to each other. To me, this seems really intuitive. So this is my example. Okay, we're up close. We're within that 6 feet social distance, unfortunately, and you have two people that are 10s. Maybe they're super attracted to each other because they're like, dang, you're a 10 and you're right here. But if two 10s are a whole football field apart, they're not going to be very attracted to each other because they're going to be really far away. Whereas two 1s super close together are like not really that attracted to each other because even though they're close to each other. This is a terrible example, but I think it's going to help you remember. I'm embarrassed even saying it. Either way, increase in charge, increase in attraction. Increase in distance, a decrease in attraction. Okay. This only works if you have opposite charges. Okay. So in the terms of a nucleus, we're talking our positive center and our negative electrons are going to be attracted to each other. Whereas if you were talking about two electrons, those are going to be repelled. So if your two charged particles have the same charge, it's a repulsion. If they have opposite charges, it's an attraction. And Rutherford's atom, my students always call this the Jimmy Neutron atom because they don't have specific paths for their electrons. Okay. Coulomb's law is important. It's something that we're going to mention quite a few times throughout the whole year. It comes up in a couple different units and a couple different objectives. So I wanted to introduce it to you now because it's relevant when we start talking about the atom. You probably don't have any questions on it on the homework for today, but you will as we go forward and talk about periodic trends next. So keep your eye out for some Coulomb's law questions. So after we had Rutherford's atom, we were noticing that different elements are releasing different colors, and that's where we knew that these electrons couldn't just be random. There had to be some kind of an energy amount associated with it, and that's how we got to the Bohr model. The Bohr model is a more sophisticated version of the Rutherford model where it says that these electrons are not just bouncing around outside, they are in discrete energy levels, okay? And when those electrons gain energy, they are going to temporarily jump up to a higher energy level. So our normal electron zooming around at energy level 1 gets hit with a jolt of energy. It goes up to level 3 until it falls back down. So those vocab words we call our lowest energy level, so like where it is naturally, is called the ground state. When it absorbs energy, it gets promoted up to the excited state. And when it does this, when it releases out, it releases energy in the form of light because the different amount of energy is going to be associated with different wavelengths. So we see different colors of lines in a spectrum. Cool. Because each atom has a different positive center, the electrons are pulled on with different amounts of energy, which is what makes every element have a different line spectrum. Elements are going to release different colors of light because a +4 center is going to have a different attraction to your electrons than a +10 center. Okay, so we're looking at Coulomb's law here. The bigger the atom, the more those inner electrons are going to be attracted to that nucleus, and the more energy it's going to take to pull them away from the center. So cool. This is what an atom looks like, right? No. The thing about science is that models are used to explain the observations that we have right now. So the Bohr model was the best they had when they came up with it. And since then, more research, more studies, more math has led us to more complex models, which includes our quantum mechanical model that Schrodinger and Einstein helped develop. All right, so this is going to be like a 3D dimensional probability map. What that means is it is the space that an electron is most likely to occupy. I like to refer to shell numbers as energy levels. A lot of textbooks do, and I find that's the easiest way to think of it. So we're going to talk about the first, second, third, fourth energy level, and then we'll talk about subshells inside of that, and then orbitals inside of a subshell, and then electrons inside of an orbital. This should ring some bells from what we did last year. Let's look. This is the organization of how electrons will fit into a atom, into their energy levels. So the first energy level can only have the s subshell. An s subshell can only hold one orbital. So I'm just reading across the top here. And one orbital can hold 2 electrons. So total, the first energy level has 2 electrons. The second energy level has an s and a p subshell. S has 1 orbital. P always has 3. Each orbital always contains 2 electrons for that total of 8. So hopefully that shows you kind of how you can read this table. So if you ever need to figure out what is in each energy level, I think this is a nice graphic that shows you how we get to those 2, 8, 18, and 32 values. All right, so we're going to be talking, I hope it's clear from this, about electron configurations. So I'm just going to talk really quick about the rules. So one of those rules is our Pauli exclusion principle. I don't think there's ever a situation where you have to name that it's called the Pauli exclusion principle, but they might ask you how many paired or unpaired electrons there are in an or something like that. So Pauli exclusion principle says that all electrons in an atom are unique. Okay, so what that means is because we have space for two different electrons in an orbital, we wouldn't want two electrons to have the same address. So like my 1s electrons, they both live in the first energy level in the s subshell in the same orbital. So the way that we make their address different is one of them is clockwise, one is counterclockwise. Hund's rule is another way of ensuring you fill your orbital diagrams correctly. So these two that have arrows drawn are actually called orbital diagrams. When you think orbital diagrams, think picture, think having to draw arrows. Electron configurations, you get to write the numbers. So the top part here is the electron configuration. The drawn out part is the orbital diagram. Okay. Hund's rule is in accordance with Coulomb's law that electrons are both negative, so that energy between them is a repulsion. So your electrons are going to want to be as far away from each other as possible. So we're going to fill one electron into each orbital first before we start doubling up. All right, our Aufbau process. So the Aufbau principle has to do with how you fill electron shells. So we're going to start at our lowest energy up into our highest. The periodic table shows us what that order is because it's not always the order you think, right? Like 3D actually has a higher energy level, a higher amount of energy than 4S. And we'll see that when we look at the periodic table. So fill from lowest energy orbitals to the highest energy orbitals. And that's going to be what I'm going to start this whole sentence over. When you start and you fill from the lowest to the highest and you're done with your electron configuration, that atom is said to be in ground state, right? You've filled in order. If it was an excited state, you could have an atom or an electron that's in a higher energy level, okay? All right. So here is a depiction of the periodic table showing you their energy levels and subshells. Okay, so this is how the order goes. You'll follow by atomic number. So like across the top first is 1s. Atomic number leads you then into 2s and then into 2p, 3s, 3p. And this is where it gets a little different. So 3p then leads you to 4s, 3d. Okay, so spend a little time with this diagram, practice some problems. I think you'll get pretty comfortable with it. And you always will have a periodic table on the exam. So like you don't have to, like as long as you remember the D block is 1 minus and the F block is 2 minus, I think you'll be okay. We talked about the noble gas method. So your noble gas core method is how you can make your life easier. So when we do electron configurations, you have to start all the way at 1s until you get to your element. If your element is down here, that sucks because you have to do 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, whatever you are ending at. But it's easier to just go to the noble gas beforehand, write it down, and then just continue your electron configuration from there. It's a handy dandy shortcut. When you do that, make sure you put your noble gas in brackets. Other than that, I feel like that went pretty well last year. And we'll do a couple practice ones, and hopefully that will ring some bells for you guys. Ions and electron configuration. So ions are when an atom has gained or lost electrons. If it's a positive ion, it has lost electrons. If it is a negative ion, it has gained electrons. So the electron configuration is pretty easy usually. You just either add electrons into your configuration or you take some away. The only thing that's new and weird here is that we always want to take those electrons out of the highest energy level, meaning like that 1, 2, 3, 4. not out of the last ones that were filled. So which means when we are dealing with transition metals, they're going to lose their outer S electrons before they lose those 3D. And I'll show you an example of what that looks like. So we're going to practice a few. And this is where it might be weird. I'm not exactly sure what's going to happen when I plug in my dot cam, but I don't really have another good way to practice this because I don't. I guess I could do it on the board. I'm just going to do it. Okay. Here's to hoping you guys can hear me. If not, I will voice over on the other thing. Okay. So, if we want to do the configuration for sulfur, we would go All right. I know you probably couldn't hear that, but that's what question sessions are for, I suppose. And now he can't see me, so hopefully this all works out. Here is my PSA for today, and this is important. So I'm going to make my not face here bigger, even though you can't see me. Oh, now you can. Serious face. Don't cheat. I'll know when you're cheating. Okay, what do I mean by that? There are some exceptions on Electron configurations that have to do with when elements want to have full or half full shells, subshells. They're great. They make sense, but it's more than you need to know. It's outside the scope of the AP test. So if you Google, what's the Electron configuration for copper, and it comes up with one, I'm going to know you're a big fat cheater head, because you're going to be using exceptions that you never learned before, and it's going to make me sassy. And I don't want to be sassy. So do the work, learn the stuff, don't Google the answers. Not that I think any of you would, and you're all lovely and wonderful, and I'm sorry for sassing you, but I will